Thank you. So, good afternoon to all of you. I welcome you all again to this next series of this talk, which we are holding as a part of the Azadi ka Amrit Mahotsav. This is a big celebration. We are moving forward with various lectures, various topics, which we have proposed to organize by Skill Council for Green Jobs. This Azadi Ka Amrit Mahotsav is a big celebration how the country has progressed till now and how we are progressing further so that we can become a super economic power. There are various areas, so many events are being held all over the country, and we in Skill Council had decided that we will interact with learned speakers, on various topics of renewable energy, sustainable development, waste management. And I can tell you the buzz today is of green hydrogen. Today we are all sitting, in a USA organized training program on green hydrogen. What are the techno-economic considerations? So green hydrogen is one of the big buzzwords, and of course it is the need of the hour. We have to move. There are various ways we can move to our 2070 goal, but green hydrogen is one which the government thinks that it is going to pave the way towards meeting this goal. And it is not only the application, the utilization, the production is the main challenge. We need to take up various activities, various pathways we need to explore, and biological production or from biomass. This is one area which holds a lot of potential, but still we are far behind in promoting or taking up these technologies, and we need a lot of push in this direction. So I always say the efficiencies are poor, but the process is very good for producing hydrogen from biomass. The gasification route is even better. So we have a very learned speaker today, Dr. Raman. I know him from Terry days, and he is going to give us a lot of insight into how this gasification process can facilitate the production of green hydrogen. So before I ask him to take the screen, I want to request Mr. PV Singh to kindly introduce him, and then we move on. Thank you for accepting our invitation, Dr. Raman, and we welcome you also. Thank you very much.
Thank you.
Thank you, ma'am. Thank you very much for welcoming the speaker. Good afternoon, everyone. I'll welcome to the 64th series of webinar. Skill Council for Green Job is organizing a series of webinar to celebrate Azadi Ka Amrit Mahotsav as a part of India's celebration of 75 years of independence. In this series, SCGJ is inviting eminent and learned speakers in different sectors on sustainable development, renewable energy, and waste management, so as to deepen the understanding of recent developments in these sectors. The first in the series was launched on 24th September 2021. Today we have Dr. Raman, Dr. P. Raman, who is a very experienced, learned, and distinguished speaker, who will be sharing his expertise and experience on green hydrogen production through advanced biomass-steam gasification technology and detailed comparison with the electrolysis process. Dr. Raman is the Director of Energy Efficiency and Environment Private Limited, New Delhi, India. Having more than 40 years of experience, acquired a strong subject expertise on renewable energy technology. Dr. Raman has done his doctorate from Pondicherry University on syngas production through biomass gasification and its applications for power generation, industrial thermal applications, and transport sector. Dr. Raman has extensively worked on several renewable energy products in the area of biomass gasification, biogas plant, cook stove, and solar pumps. Dr. Raman recently developed an advanced three-stage biomass gasifier system for power generation and got it patented. He worked in many international projects in the East Asia, Africa, Europe, and Australia. Dr. Raman contributed to more than a dozen patents on the inventions of renewable energy products. Dr. Raman published more than 100 publications, including international journals. Presently, Dr. Raman is focused research or design and development of biomass-steam gasification systems to produce hydrogen-rich syngas for production green hydrogen, development of high-efficient and clean combustion biomass cook stoves. Now I'm requesting Dr. Raman to start the presentation. Over to you, Dr. Raman. Thank you.
Thank you. Thank you very much. First of all, I would like to thank the team SCGJ for giving me this opportunity to talk on this subject, green hydrogen production. Actually, and also I would like to thank all the participants joining the webinar. And I will talk on green hydrogen production through advanced biomass gasification technology and a detailed comparison with the electrolysis thing. Because mostly nowadays, any literature in this thing we see is that electrolyzer based the green hydrogen is more focused actually. So then I thought, and biomass also a potential renewable energy source for production of green hydrogen and also very high efficient. Then I thought I will give a small speech on this one. And again, biomass gasifier is originally started for mostly it was focused on the thermal and power generation application. I will briefly talk about the challenges and about how the technologies evolved and where do we stand and how to go about it. And also now, apart from that power generation or thermal application, now the green hydrogen production is another branch which is opened for this biomass steam gasification technology actually. So detailedly, I will try to touch that how it compares with other existing technologies again actually. The outline of the presentation is like this actually. I will start with some introduction on the need for biomass gasification for power generation and hydrogen production actually. And about the biomass gasification technology, what all the technology exists and their merits and the challenges kind of this thing. So generally, there are several challenges because it's a very old technology, but still the biomass gasification is not getting that much popular because of several challenges in the technology. And again, the biomass is a heterogeneous fuel. Actually, it has a different biomass has a different characteristics. So I'll talk on the types of fuel and fuel flexibility requirement again actually. Advanced three-stage gasifier. There are several types of gasifiers, and I will also talk about the advanced three-stage gasifier, its features, and how it differs from other gasifier, and what are the advantages kind of thing. And again, the types of biomass waste which can be used for gasification. Then particularly, I will talk a little bit more on the containerized gasifier system for power generation. For example, when we go to this East Asia or Africa and everything, and gasifier is basically we want to use for the decentralized applications. And everywhere we cannot expect that skilled people will be there for installation kind of this thing and installation of the infrastructures required for installation. So containerized gasifier is one of the way out to come out of those issues. And again, the green hydrogen through biomass steam gasification is another thing which I will compare. So I will compare with the electrolysis and within the biomass gasifier things, what all the type of gasifiers and how their hydrogen richness in the syngas. Also, I will discuss on those part. And the hydrogen color codes. There are several colors has been given and based on their process or the source of fuel. So in fact, when I was preparing this thing, came to know there's different colors. When the presentation comes, you also will be noting down there may be almost it covered all the colors actually. So hydrogen rich syngas actually, that is the key word of this entire presentation. Then we separate the hydrogen. So in this entire presentation, I will tell that focus is there on that how biomass-steam gasification to produce hydrogen rich syngas close to 50 to 70% actually. And there are beyond the presentation or beyond this thing. One is the gasifier produces the hydrogen. The second and third stage, the other technology to get in is that hydrogen separation and hydrogen storage, hydrogen transportation. They are the additional things which are required for the complete supply chain management again, actually. So, but on this presentation will be focused mostly on the hydrogen production part, actually. So, included in this presentation. And choice of utilization and its efficiency. We produce the hydrogen with a lot of difficulty, with some certain efficiency, energy input, right? There are certain things actually. Then how efficiently we use it, that also there actually. Produce 2 kg of hydrogen and one is using a 25%, another is using 50%, mean then the end result is entirely different. So one is the production efficiency, another is the utilization efficiency. This both I will talk on the things actually, so that this will be helpful for us to decide how to use and where to use kind of this thing actually. So choice of utilization and its efficiency is one of the important factor. And also a comparison of the hydrogen production cost, because this may be earlier stage for the as far as the biomass is considered, because nowhere we could see that the biomass is to green hydrogen. I might have come across more than 400, 500 publications actually on this subject, but this hydrogen from biomass is not that much, at least the green hydrogen. Yes, people talk about syngas, but not beyond that one. And the separation cost and storage cost has to be considered. So, but still we can get talk more on the production cost side actually. Then conclusion, how to the way forward, how to go about with the existing status of the technology and what is next, kind of this thing. So that's how I will cover the presentation, and whatever is the questions and all, at the end I will try to answer whatever is possible. The introduction, need for biomass gasification. Why do we need gasification actually? First of all, gasification is what the biomass is used since many years. Even that was the first primary energy used actually, when even in the Stone Age, and for cooking or heating or whatever it is. But hello. Okay. So biomass is the renewable energy source and it's carbon neutral. That is one thing. And see, when we burn the biomass combustion in open space, it's a complete combustion. That's what we call it. Every kg of biomass requires about 6 kg of air, and the oxygen in the 6 kg of air is required for the complete combustion actually. So when we in the cook stoves and boilers and furnaces and all, we give that either the same 6 kg or more for combustion. So it's a complete combustion. We don't take the gas out separately in that one. But in biomass gasification, what we do is it's also called as a partial combustion. In partial combustion, we don't burn the biomass completely. Basically, 10 to 15% of the biomass is burnt, and 85% of the biomass is converted into combustible gas. So that is the gasification process. So then again, the cleanliness, environment effect, efficiency, and all things when we see, the direct combustion and overall efficiency cannot exceed more than 15% or 20% actually in the furnaces. And that I'm telling about power generation part. In cook stove and all, it goes up to 40%. The good gasifier-based cook stoves. And what happens is, when you convert the biomass into gas is fuel, then we have a good control over the power, at the same time the clean combustion. That's where the biomass gasification, need of biomass gasification is there. Global energy contribution by biomass is 10 to 14%, and biomass is even now used widely for cooking and water heating application in most of the things. Even space heating also, in some of the countries they use it actually, because nowadays they are shifting to pellets, and particularly in the remote and rural areas, 90% of the total energy demand is met by biomass. Also, it's not only the reason mostly many people are using biomass is its low cost. Sometimes even nil cost. In agro residues and all, people collect directly from agriculture field and then they use it. The cost, expenditure and all, cost management, financial management, this makes a lot of things. It makes the necessity to use the biomass particularly, because everyone must be knowing that we have a very big program on giving LPG cylinder in the rural areas, but still, if anyone go to the house, you will see the LPG cylinder. Next to the cylinder, there will be a biomass cook stove. So that's where it comes as the cost plays a big role there, actually, biomass. And so economically and at the same time, it's efficiently one of the good technologies, the biomass gasification is. Gasification is more than 2 centuries old. Why I'm telling this thing here is the focus again, that how much important we give or how much we focus on it to develop it more and more. Because so far, somewhere it goes on the background and only few people are working on it. And particularly in 1926, when the oil price was gone up, then a lot of work has been done on the biomass gasification. That is during Second World War. I think that after that, the focus has come down, and some research institute here and there is working on it, and some demo system has come out, and it has not come like PV or wind. That is the one of. That's why I'm telling you, it's more than 2 centuries old, but still it is there. We need to how to say, we have to focus, or we have to realize, or we have to recognize what is the advantage, disadvantage. That this presentation will help on that direction, I think, to use the biomass energy more efficiently and other things. And access to electricity is essential for economic growth and development, because once the electricity is there, many things gets in the industry and everything particularly. And so biomass gasification is focused more on the for electricity generation, particularly distributed generation. And there are some plants, even grid connected biomass power plant at large scale, but could not come see a major impact on it. Due to several reasons, actually. Yeah. So now, and the electricity is one of the major application, because this presentation will focus on two things. Initially, I will touch upon that electricity part, and then I will get into the green hydrogen part. Because now the green hydrogen is talked a lot, and there are many things. Now, recently, India also has come up with the green hydrogen mission and all. So then we will see that what is the role of biomass gasification in this thing, actually. Power generated through biomass gasification can be used to reduce use of fossil fuel, actually, because once it's electricity, even the battery car, transport, whatever it can be used for it. And it's high efficiency. Again and again, I am talking about the efficiency. The efficiency wise, because 85% is the energy conversion efficiency of a biomass gasification system. And almost 95% is the mass conversion, actually. So when we do a mass balance analysis, 95 to 96% of the weight is converted into the gas. And in energy part, if you see, around 85% of the biomass is converted into gas. So which is available, because we don't lose too much energy on the gasification process. Yeah, just before getting into it, because most of us may be knowing, and it may be very good, because people who are our audience, who are, it is our new to the technology, or want to know more about the gasification process, I thought that I'll put the basic three basic design of biomass gasifier technology. And there are some more systems also there, but these all are the very popular one. The first one, when we see, it's called as a downdraft gasifier. The downdraft gasifier is, they put it the direction of the fuel flow. Fuel flows from the top to bottom. And again, the biomass is fed here and the air is given from at a reactor. Then the gas comes below the reactor and the ash falls down to the bottom of the gasifier. The gas is drawn from the gas. So the biomass is fed from the top and the gas is drawn from the bottom. And the gas flow is from top to bottom. So that's how they call it as the downdraft gasifier. This also called as the co-current gasifier. In this gasifier, if you see, the fuel flows top to bottom and gas also flows top to bottom. So then it's called as a co-current gasifier. In this gasifier, the reaction temperature is quite high and the gas doesn't go to the low temperature zone again. The temperature, if you see, drying zone will be around 50 to 60 degrees centigrade and pyrolysis will be around 300 to 400 degrees centigrade. And the combustion gasification zone will be around 1000 to 1200 degrees centigrade actually in air gasification. So then gas comes out at a very high temperature, and so most of the volatile matters, particularly tar and other materials, are converted into gas. So the tar content, tar is the impurity comes along with the syngas. That is the one creates a lot of hindrance in promoting this technology and all. I will talk more on the thing, how it is being tackled. So this is the downdraft gasifier. And since the tar content is less in this gasifier, and this gasifier is very much popular. The another model is called as updraft gasifier. Here the biomass flows from top to bottom and the gas goes from bottom to top. You can see that the biomass is drawn, it's fed from the top and the gas also drawn from the top. So that's why it is called as updraft gasifier. Here if you see the combustion reduction zone, the high temperature zone, the gas is produced here, but it comes through the low temperature zones like pyrolysis, drying and all. This is the zone, the pyrolysis zone, a lot of tar is being produced actually. So it carries the tar content is very high, almost a 10 gram if you see in the quantitative way. It's around 10 gram of tar per meter cube of syngas. The downdraft will give 0.1 to 1 gram of tar in the gas. So it is almost 10 to 100 times higher comparing to the downdraft gasifier actually. Then third one is it's basically used for thermal application, particularly it's called as cross draft gasifier. Biomass is fed from the top, and in the reactor, air is given from one side. Just opposite to that, a gas is drawn actually. So hence it is called as a cross draft gasifier. Here the drying zone is, you can see the geometry of the drying zone and combustion zone, everything varies here. It produces good gas, almost equivalent to this updraft gasifier actually. But the tar content will be slightly higher. That's why it's very rarely used system cross draft gasifier. And somewhere they use for updraft gasifier, particularly for loose biomass and coal gasification and all. And downdraft gasifier is popularly used. And in the entire presentation, we will see about downdraft gasifier. There are some other gasifier called the fluidized bed and all that we will not touch in this thing. That is, then it will become a complete on gasification presentation. Challenges in biomass gasifier. I have put some of the key challenges. Gasification technology is older, but still due to the challenges, it could not come up. In the beginning of 20th century, charcoal gasification was used. That time, as I told earlier, they used the gas from the charcoal to run cars and buses actually, even trucks and all, because that time there was a oil crisis. And maybe similarly, anytime the oil crisis or the ban on use of conventional fuel, petroleum fuel, then the again gasifier may get its place. Basically. When there was shortage of diesel, they used the syngas for not only for the car and buses, but they also used for street lighting actually. So it was used, but it was not continued due to several other alternative and other this thing actually. The main problems associated with biomass gasification system are quality of the gas, presence of impurities like tar and dust. So the gas comes from a firebox. When we fire the biomass, the ash particles are released, and also some of the due to incomplete or some partial gasification process, some volatile matters is converted into tar, and so the tar is coming. The tar is the most how to say most affecting part in the gas, because suppose if we put it in the engine, it affects that all the carburetors and cylinders, valves, and even the lube oil. So then a lot of standard has come, how much torque can be allowed. Some people in between, I think during 1990s, some even Manari has published some books on the thing on standards. 50 mg or something was allowed, but even 50 mg, in my practical experience, if you go for a 250 kilowatt or 500 kilowatt system, which consumes around 1000 meter cube per hour, 50 mg means that goes into many grams actually. So engine will be filled up with the tar, even 50 mg. So what we are looking for is ultimately no tar gasifier. If the tar is not there, it's a very good gas like LPG or CNG. It can be used for either engine or any applications actually. So variation gas quality along with its operating capacity. Then again, that gasification system works on, particularly the gasification reactor works with on a certain temperature. When you burn more biomass, the temperature is high. When you burn less biomass, when the temperature is less. Because the gasifier capacity is given like, let us say, like 100 kilowatt system that will consume about 100 kg per hour. The same generator, if you operate at 20 kilowatt or 30 kilowatt, it comes to the 20 kg per hour system. So a 100 kilowatt system, if you operate at 20 kg per hour, then the reactor temperature falls down like anything, then the tar production increases, the gas quality is being affected. So the quality of the gas is directly proportional to the capacity, operating capacity rate of the system actually. So that's why some people even put it, their name as turn down ratio. If we design a gasifier for 100 kilowatt, means the 30% or something like that, we should not go below the 30% to maintain a certain gas quality. So in that way, if you see is a 100 kilowatt system should not go below 30. So at least we maintain the temperature to the minimum possible actually. And also the engine efficiency also affects a lot when we operate at the lower load part, low capacity load. So it's better to operate at the higher. So there is a variation in the gas quality depending on the operating condition. That is one of the biggest challenges. So it has to operate at a certain, generally above 80% operation is very good for gasifier as well as for the engine. And it also needs skilled operators for operation maintenance. And now there are works are going on, automation or semi-automation actually. In the beginning, the gasifier demands for the skilled operators, because otherwise it's very difficult, because it is very complex systems. It has many components that I will come to know at the latter part of the presentation. So skilled operator getting everywhere is not possible actually. Demand for automatic system for continuous power generation. Because, if it is a continuous, means it's very difficult for people to stand there and see what is to be done. So it's ash removal system, fuel feeding system, and even the engine control, everything needs automation. That is one of the important part. It's a demands automation. And in fact, some countries, the manpower is too expensive, then it affects the economy of power generation using biomass gasification. So disposable of waste generated from gasifier system like tar and wastewater used for gas cleaning. So for the gasifier systems which produce the tar, then even if they clean, then the tar absorbed in the cleaning medium, disposal becomes a problem actually. So there are several challenges, and how it is addressed, and unless until we address these challenges, it's difficult to take it. So it's important, because trouble-free system and user acceptability system is very important for taking any technology forward. We talked about the tar part. What is the thing that is the one created all kind of problem, and what is the method? There are certain method, because everyone across the world, most of the countries are working on this biomass gasifier still at demo system or some commercial system, but not on a big scale. But still, the tar has to be removed, and people are using different type of tar removal systems actually. One is the water scrubber. Simply spray the water and pass the gas through it. That is mostly adopted system. But what happens is after a few hours, the water gets contaminated. Then it demands for a water treatment, or disposal of the water becomes the problem. That is the one, the water scrubber. Then diesel scrubbers. Some people even use the diesel scrubbers and sand filters. So if these things absorb the tar, means disposal is a problem actually. And chillers to cool the gas. Chiller cools the gas and removes the tar, but at the same time, the cleaning the chiller itself is a biggest problem actually. Then also the electrostatic precipitator, because this is mostly used actually. Some people for the engine application, see what happens is you use any of this technology and then at the end they say that no tar gasifier again. But it's not like that. Any cleaning mechanism will have certain efficiency, 75%, 80%, 90% like that. And none of the this cleaning system is 100%. And again, so this is very much important to remove the tar at the source itself. Actually, the gas produced from the gasifier should not contain any tar. Actually, so removing the tar and managing this the contaminated all the tar removal medium is also a problem actually. So all these tar removers have a performance efficiency. As I told that the removal of tar at the raw gas itself is the ideal part. One is on the gas quality part, and again another part is that fuel part actually. So, biomass fuel is quite a lot of variety of fuel. Fuel wood, initially people were using fuel wood, then later wood has become very costly, and so then it's we have to look for alternative biomass fuel feedstock, that is like MSW or agro residue kind of this thing actually. So there is a large variation in the biomass characteristic, but it will depend on the source of the fuel, different type of the biomass. So if you see the coconut shell, corn cobs have a very good calorific value, almost equal to fuel wood, but they vary in the physical properties like bulk density and void fraction and all. If a completely packed bed, the reaction cannot be taken place. It needs a certain surface area, certain void and all. And again, the low density fuel cannot flow freely down towards the reactor. So the density for syngas production, the biomass should have at least 250 to 350 kg per normal meter cube. That's what they say. And if you see that some of the loose biomass will have 100 to 150. So there is a different type of approach has been taken in the fuel hopper design, so that the fuel flow is one of the important part. That's what the ultimate this thing. The rice husk is one of the abundantly available fuel, particularly in many countries in East Asia, Thailand, Cambodia, Vietnam, and all those countries. And but its density and ash content was the barrier. So it requires a specially designed ash removal system particularly. And municipal solid waste also can be used, but it is in the pelletized form. Because of the density, to compensate the density part, it has to be used in the pelletized form for gasification. And high ash content biomass waste needs a specially designed ash removal system. Recently, we designed the ash removal system. There are different kind of ash removal systems are there, something like rotating grate and oscillating grate. There are many types of grate and vibrating grate. So the ash, if the ash accumulates in the reactor, then it affects the gasification process, actually, the gas quality. So continuously removing the ash with proportion to the gasification part, the ash generation things, because when the rice husk is having about 20% of ash, wood is having less than 1% of ash. So same ash removal system will not work for every gasifier. So it's important to have a specially designed ash removal system depending upon the fuel, or we have the maximum limit and adjust the ash removal system according to the fuel grade. So gasification system also should have with fuel flexibility to use different type of biomass. So one gasifier which can use any type of fuel is the ultimate requirement actually. Because if we have 10 or 15 type of biomass, and one can go for many gasifiers actually. One gasifier, multiple type of biomass feedstock. Acceptability is important part again. Now I will talk on this. This is the gasifiers technology developed by Energy Efficiency and Environment Private Limited. This is known as, we called it as advanced three-stage gasification system for power generation using multiple type of biomass. From the title itself, we can see that it can accept multiple type of biomass fuel. And see, there is what is advanced three-stage gasification system? Because those gasifiers which are shown in the beginning, the three type of the downdraft and updraft and cross draft gasifiers, they all are single stage gasifier. So air is fed at one place and the reactor is combustion and reduction takes at once basically. And then again, two-stage gasifier has come. In two-stage gasifier, they are separated and gas is much better comparing to the single stage. This is a three-stage gasifier. So it's a first stage, it's produces syngas, and another two stages refining of the gas actually. The residual impurities like tar and all being converted into gas. That is the way we call it the advanced three-stage gasification system. And this is a patented technology, and last year the patent was granted for it actually. And these are the different kind of biomass which we can use in the rice husk, coconut shell, or cotton stalk, not cotton, again, groundnut shell. So anything actually it can be, because since it's three-stage, it gets a pyrolyzer and then the gasification 1 and gasification 2 and 3 kind of this thing basically. Because when we talk about the biomass for energy generation, we should not think about which biomass kind of thing. So that question has to be eliminated. That was the main objective of it actually. Any biomass, it should be dry and other thing that can be done. Actually. So salient features of the ATS gasifier system is, one is the multiple inputs, and again the zero tar. This gasifier, being the three-stage gasifier, doesn't produce tar. So a lot of cleaning, the tar removal equipment can be eliminated from the gasifier system. So the number of components used for tar removing comes out of the system. And cleaning is much easier because even the dust remover, because the bag house filter we use generally in the conventional gasifier system, that bag house doesn't remove only tar, only dust, but it is supposed to remove the dust, but that also will get, a lot of tar will get accumulated. So cleaning and reusing becomes a very big problem in it, actually. But particularly in this ATS gasifier, that baghouse filter is completely eliminated because only dust is removed in a different way and tar is not there. So that is zero tar and low maintenance. Because of the gas quality, the minimum impurities and no tar kind of this thing, the maintenance is very low and sustainable and durable actually. Because of the, we don't need to bother much about the operation part. So it's a long duration operation can be done. And also the system is completely made on stainless steel. This mild steel is getting very much corroded very easily because of the various products generated in the gas actually. The condensates on this wall easily erode the gasifier material, particularly mild steel. So the entire gasifier is made of stainless steel, so that it's very much durable kind of this thing actually. And easy installation, I told that the system is it can be easily installed because it's a containerized system, a quick installation. Within 2 to 3 days, one can install the system. Otherwise, the installation of the system in the conventional route takes 15 to 20 days actually. Very major points of the process flow of this ATS gasifier is collection of the locally available biomass waste, processing of biomass through ATS gasifier system to obtain high quality producer gas, and cooling and cleaning of producer gas using an environment friendly compact gas cleaning system. It has a heat exchanger And basically, there are several heat exchangers. The gas temperature is brought down from 600 degrees to ambient temperature, close to 30 to 40 degrees centigrade. Actually. To generate electricity by feeding the producer gas into IC engine, 1 kg of biomass is needed for 1 kilowatt hour of electricity, actually. So, particularly when we talk about IC engine, there is no engine specially designed for producer gas or syngas. We use the natural gas engine. Natural gas combustion property and syngas combustion property goes very much closer. So natural gas engines are generally used for power generation using biomass gasifier. And supply of electricity to the industry and office premises and residential is possible using this high quality gas and natural gas engine. Actually, it's just a view. I thought I would show you that a dual fired gasifier system in the field. Actually, this system is installed in Thailand. Actually, Thailand, when I was in Terry, I installed 2 systems, and in Cambodia also similar systems were installed. Actually, we can see that. The biomass gasifier system, and there are several cooling systems. This is the backup system, and in the ATS gasifier, backup system is removed, and the cooling cleaning system becomes compact. The container is the ATS gasifier system is the view. Actually, it's a computer generated view, a representative view of the system. Here, if you see the main gasifier unit, and it has a heat exchanger. See, the gas comes out of the gasifier is around, I told, around 600 degrees centigrade, actually. And normally in all the gasifiers, this energy is gone. The sensible heat of the producer gas, syngas, is gone into that water scrubbers, particularly. Here, what we do is we take the energy, the thermal energy of the hot gas to heat the air. So gasifier is provided preheated air at the temperature around 300, 350 degrees. So these all are the things, the several improvements. That is the one is going to enable green hydrogen production from the biomass gasifier, actually. So when you produce the high temperature air, instead of providing the air at 30 degree or 40 degree, if you provide at 300 degrees centigrade, so the firebox temperature increases, actually. Instead from 900, instead of 900, it will work at 1200 degrees centigrade. Then when the firebox temperature increases here, then the tar is cracked very well, then the tar is removed. So there is a reactor, and then when the first exchanger, heat exchanger, at the outlet, the gas comes around 100 or 125 degree. Even if you put 400, 500 degree inside this heat exchanger, the gas comes about 100 degree. So, but that also not suitable for to put in the engine because of the volumetric problems. Then there is a dust remover, and then it goes to another heat exchanger. There are 2 more heat exchanger. In those heat exchanger, gas is indirectly cooled because generally people pour the water on the gas in this scrubber system. But here in the heat exchanger system, water is passed. It is a shell and pipe heat exchanger system. Water is passed in the pipe, and the gas goes through. Actually, that's how it is cooled. So after getting the 2 heat exchangers, the gas is cooled very close to the ambient temperature, actually, around 30 degrees or something. Then it has put a safety filter, then it goes to the engine. In the container system, if you see this container system of 125 kilowatt system and up to 200 kilowatt system, we can have the system in 3 containers, actually. That engine goes in 1 container, and the gasifier system and cleaning system goes in 1 container. But there are some places continuously rain and difficult to dry the fuel, wood, or the biomass. There, what happens is that the 3rd container is having the complete drying system, actually. The biomass is being dried using the engine exhaust heat. So this is a complete system, actually, fuel drying and fuel charging. And here the system, most of the thing has been atomized, actually. Automation is very much important. There are fuel sensors and ash sensors and all to remove the ash kind of this thing. So once when we have a easily, how to say that, without human involvement, if system works very well and the economy also comes down, then the people, anyone will accept the use of the system. Actually, the gasified technology can be used in a large scale. So on the power generation part, if you pick up the three key points, biomass waste is a potential source for decentralized and distributed power supply to meet electricity requirement of the domestic and industrial sectors. The advanced three-stage gasification system is designed to gasify multiple type of biomass waste to produce high quality syngas for power generation. And the container system overcomes the challenges related to the field, about installation and infrastructures and skilled manpower requirements, all these things, because it leads to a significant time reduction in installation. Now, we see originally as I told, actually, the gasifier was focused on the power generation part. And now the focus is also added the multiple use of this biomass gasifier. Another application is the green hydrogen production using advanced three-stage biomass-steam gasification system. Why I'm telling green hydrogen production using advanced three-stage biomass-steam gasification is, if there is tar in the syngas, it cannot be used for hydrogen production, because the hydrogen from the syngas has to be separated using gas separator like a PSA, pressure swing adsorption system. That's what we will talk about it. And they need very clean gas, actually. Otherwise, it can affect the gas separators, actually. So if it affect the gas separator will not work, actually. So if we want to use biomass for green hydrogen production, then the gas should be tar-free, absolute zero tar, actually. So that is one of the basic requirements. That also was one of the reason not much people are talking about green hydrogen from biomass, actually. But the technology evolves, and there are many possibility occurs. Now, when we talk about green hydrogen, see, though the topic is on green hydrogen, we'll talk about the color codes of the how the hydrogen is coded. In olden days, then the TV screen, when we control the cover, the color of the screen, actually, when we adjust, there will be a color bar will come, actually. Because when I saw the thing, that's what I was remembering. Almost how much 3 plus 3, 6, 9, 10 colors are there, and hydrogen is coded. I gave it. I won't go much in detail on that one, but if you see the green hydrogen and gray hydrogen, blue hydrogen, these three are very popular. Brown black also, it's conventionally for fertilizers and industries and all. Brown and black hydrogens are made out of coal. Depending upon the coal, the colors are given. So first 4 colors are very popular. And if you see, the blue hydrogen is basically represent the hydrogen produced from the conventional fuel, and also has the carbon capturing and sequestration or utility kind of this thing. So if the carbon is not put directly in the atmosphere from the source fuel, then they give it as the blue hydrogen, actually. So, but presently the gray hydrogen dominates around 96%. Only 4% is closer to 4% is from the green hydrogen. So now now we can imagine how far we have to go to have this hydrogen future, hydrogen economy, and all, from 4% to, I don't know where we will go, but we are the starting point now as on today is around 4 or 5% actually. So here the gray hydrogen is produced from natural gas, and the brown black is produced from the coal. And both of them, if they have the carbon capturing part, then those hydrogens are turned into blue hydrogen. And all the hydrogen produced from the renewable energy, like so far, wherever, which book, any book we turn, it says that solar and PV and through electrolyzer part, actually. And the biomass also comes here, because the definition says that hydrogen produced from the renewable energy sources, actually. So this is just for an idea that the different colors of hydrogen, and we will talk more on the green hydrogen part, actually. uh, production of this hydrogen-rich syngas through biomass gasification. When we say this, if you see gasifier produce syngas, the hydrogen content in syngas varies depending upon the type of gasifier and also the feedstock and all those things. I will talk some, see, there are several types of gasifiers. I will talk some of the gasifiers, how the hydrogen-rich syngas is produced. Because this is the basic point. When we talk about green hydrogen from biomass means, this particular slide is more important to take the choice of technology, actually. And again, if you see the syngas generally has hydrogen, CO, CO2, methane, and nitrogen if it is the air is used for the as a gasification agent. And if we use oxygen as gasification agent, then there is no nitrogen in it. Most of the gasifier popularly used for production of syngas is the air gasification, not even steam is added. Any gasifier, if you see, is the conventional or the even most of the gasifier, they are biomass gasifier using air as the oxidation agent. Okay, the 21% of the air when we take, we also put 79% of the nitrogen inside the gasifier. That takes a lot of heat and it comes in. So that it plays a lot of, it's a big, how to say, demerit particularly, and it reduces the firebox temperature. Also, if you see here, the first thing, the air thing, the combustion fraction is around 41, around 42%. More than 50%, close to 60% of the syngas is non-combustible gas. This is the one thing which is to be noted, actually, which has to be seen, because everybody thinks syngas burns, that's all actually. But how it burns? It burns with a 40% combustible gas and 60% non-combustible gas. Then what to be done? Then we have to improve it, or we have to go for a newer technology and all. So then what happens is, when we go for the oxygen gasification, once the nitrogen is removed, around 50% of the nitrogen is removed, 46 to 48%, then the other components becomes almost double, actually. A fluidized bed reactor, which is used oxygen as the gasification agent, gives around 46% of hydrogen and 22% of CO and 26% of CO2 and 8 to 12% of the methane again, actually. But again, at the last column, the tar, if you see, it is 4.5 gram per meter cube or 4,500 milligram per meter cube. In air gasification, we can see here I put the 1,000. 1,000 is the minimum part, and because there are many gasifiers which produce 1,200 gram, 1,200 to 2,000 gram, sorry, 1,200 to 2,000 milligram per meter cube, actually. But here also 100 is also a very large number. So that's why we will see that how to see that most the maximum hydrogen content and no tar kind of this thing, actually. Now, so we can see, we have seen that fluidized bed reactor with oxygen as the gasification agent, we can go up to 46% of hydrogen, actually. Then the next part, air steam gasification is the another part. In air steam gasification, one can go up to 27% of hydrogen and 14% CO and 15% CO2. The nitrogen becomes around 95%. Now, the same gasifier, instead of air steam oxidation, if we go for oxy-steam, actually, oxygen and steam, that is the remove the nitrogen part, actually, then the maximum hydrogen goes up to 49%. So that's almost 50% of the syngas is hydrogen here. So that has to be separated using PSA, that's what we will call the pressure swing absorption system. And once we separate it, the remaining gases like CO and methane also adds the CV to that thing, actually. Here, these gasifiers almost close to 50% of It's not 50%, 50 mg of tar per meter cube of gas actually. So that is also is a problem in the gas separating unit actually. Now, in oxy-steam itself, using another reactor called a sorption enhanced reactor, in that one, if you see that hydrogen content goes up to 73 actually. 73% of hydrogen is a very good gas, very good syngas actually. Very small, very little CO, very little CO2, and methane is quite high there actually. And but what is the problem here? When we have 73% of hydrogen, we have a very good syngas in it. But you can see the tar content is 10,000 mg, 10 gram per meter cube actually. The more tar is more problem for the gas. So how to take it out? See, it has got in such a complicated compound. So separation of hydrogen. See, in biomass steam gasification, separation of hydrogen should be made possible. That is the main thing. Now, in ATS system, the finally what I come here is the ATS system. If you put instead of nitrogen air gasification, put oxygen and steam, then the gas composition will work out like this: 49% of hydrogen, 27% of CO, 23% of CO2, and 1% methane. Here also in this graph, we can see, in this table, we can see when the methane content keep on reducing, the tar also will reduce actually. That's why that updraft gasifier which produce more methane, produce more tar. And downdraft gasifier produce less methane and less tar kind of thing. Generally, the gasifier experts say that tar content is directly proportional to the methane content in the gas again. So, and there is no tar. So we here in that today's presentation, this is my focus point here. It is possible to make green hydrogen using ATS axis steam gasification system. So 49% of hydrogen and 27% of the CO. So, and no tar. So it can be, PSA can easily get operated. If you see the process flow of green hydrogen production through biomass steam gasification, biomass and steam is put into the advanced three-stage biomass steam gasification system. Over here also that oxygen is the gasification agent. And we get hydrogen-rich syngas 47 to 49% actually, and CO. This is the calorific value of the gas here before separating hydrogen is 2630 kilocalorie per normal meter cube. There, we pass it through the pressure swing adsorption system for hydrogen separation. What happens here is the hydrogen is separated, and then it goes to the compression, storage system, and for end-use application, transport and everything. Now, what is the residual here? After separating the hydrogen, the residual, if you see, it's very CO-rich gas, 62% CO. CH4 comes almost close to 10%, and CO2 comes 28%. Still, the calorific value is 2295 kilocalorie per normal meter. This is a very good gas to operate engine and power generation. What happens is this PSA system will require a lot of power. And again, the steam generation also needs some heat. So this gas, the residual gas, will be used for steam generation and electric power generation, which is required for the system. So we don't need to put any additional energy into the system as a parasitic load or whatever it is to support the system particularly. So the residual gas is will take care of those things. So electrical energy produced here will go for the PSA, and also electrical energy will go for the compressor and storage system actually. So that's how it's a very comprehensive green hydrogen production system using ATS biomass gasifier. So here some of the numbers actually. What is the specific fuel consumption and fuel equivalent actually to produce 1 kg of hydrogen? If you see hydrogen from coal, when we go to the coal, when we think about the coal, then 7.6 kg of coal is used for hydrogen production actually. And if you think about the natural gas, it is about 4.5 normal meter cube of gas is used per kg. Hydrogen from nuclear energy and other hydropower or the PV, wind and all those things needs around 58.8 kilowatt hour per kg of hydrogen. This one number generally average is around 50 kilowatt hour of electricity is needed to produce 1 kg of hydrogen. And they also say that the range is 40 to 60, but most of the figure is above 50. And there are some research is going on to lower down the number. We don't know when it will come down. So, but the electrolysis process takes around more than 50 kg kilowatt hour per kg of hydrogen. Then we go to biomass steam gasification system. Almost 10 kg of biomass is required per kg of hydrogen produced. It can be even much lower also, around 8 to 10 kg, but I took the higher value. And on an average, about 3 gallons of water is needed to produce 1 kg of hydrogen. In biomass steam gasification, it's around 2.5 kg of water, 2.5 kg of water is required for 1 kg of biomass like that. Then 1 kg of hydrogen can potentially displace 4.35 kg or 1.58 gallon of gasoline. So this is a general figure what I told you for understanding how much energy we spend to produce hydrogen. At the same time, how much energy it gives to us again. Efficiency here, we will see that the hydrogen production efficiency by various sources actually. Some of the number, I won't go too much in detail in those numbers, but in compare, I will talk about 5 technologies. One is the photovoltaic, wind turbine, biomass steam gasification, natural gas reforming. One more thing has come that I will just remove it actually. See what happens is in there is some typo. On photovoltaic, let us talk about the photovoltaic part. It gives around 14% of the efficiency from the energy input to the hydrogen production part. Wind turbine gives at 35%, and biomass steam gasification gives 79%. Natural gas reforming is 78%. If you see here, now most of the hydrogen is produced from natural gas. This is for coal actually, natural gas and coal. If you see that from natural gas, we get around 78%. From biomass, we get around 79% actually. It's still almost similar, but still it's much better than that one. And there is a lot of scope for improvement. But if you go for coal, from coal, it is around 62% actually, hydrogen generation. So out of this, all the 5 popular this thing, and the biomass steam gasification works much better. And these 2 are electrolysis process, photovoltaic and wind turbine, and others are thermochemical process actually. And just for a comparison, those numbers I have put here in this graph, efficiency of hydrogen production, a comparison. So biomass is close to 80%. This natural gas also like that, but coal is 62%. And wind turbine and photovoltaic is not that much high, and due to that large electricity consumption and the efficiency constraint of the electrolysis. Here I gave a little bit small comparison. It gives a very, how to say, thought-provoking kind of this thing, and also I don't know how to say this thing, but this is the fact also again. When we have the electricity, and one way of using electric car with battery storage, another thing is convert the electricity into hydrogen and then use a fuel cell for the car. So one is using electricity to hydrogen and then fuel cell and then the mechanical energy. Another one is directly electricity, battery storage and the mechanical energy actually. Here, if you see, instead of going very much down all these things, I put the electrical 52 kilowatt hour, all those things. You can see that, for example, around 50 HP car engine, this has been worked out, 34.4 kilowatt hour to produce through the battery part, and similarly close to 34 kilowatt hour from the fuel cell, hydrogen fuel cell part, the overall efficiency comes 66% when using the battery car. And if you use the fuel cell and the hydrogen through route, it is 28%. Almost less than half, actually, because this is one of the things which we should know how efficiently utilize and where we want to utilize. Accordingly, we have to see it actually. So hydrogen car means where from the hydrogen comes, that we have to see actually. We earlier in slide I have put higher efficient conversion or higher efficient production of hydrogen. So we should produce the hydrogen efficiently and we should use the hydrogen efficiently. That's what the key focus of this presentation or the subject also actually. Here, this one of slide, just I thought I will put it, cost comparison of hydrogen from various processes. Actually. If you see, why I have put this slide is natural gas with CCS, coal with the CCS, low carbon electricity, natural gas with CCS, and coal with CCS, and low carbon electricity. See, what happens here is, nowhere biomass in this picture. This is not only for this graph, I am telling you. If you see any paper, any publication, any report, rarely the biomass is seen. This is one part. Another thing what I want to say, this is the 2019, this side is the 2019 present scenario. This is the visual scenario for 2060 actually. But not much variation. And here if you see that the cost of the natural gas or the coal, this all remains almost in the same band, somewhere here only actually. That's what I want to just convey the message. So we should not omit or neglect biomass. Biomass is also a potential renewable energy source for the green hydrogen production. And in fact, much better when we compare to anything. But one way we have to see that we can use many technologies to meet our demand requirement. And again, there should not be a question like, what is the potential, where from you get the biomass? Even when this kind of technology, one can create potential actually, energy plantation, and there are many other things. Even now, the available biomass waste, I don't think it is completely utilized or kind of this thing actually. Even if it is there is a demand, this also can be generated actually. And it's a table, the same thing what we have seen. It's a average number for the hydrogen production cost through various sources. Green hydrogen from PV power is around 3.4 and all. And comparing to all those things, the green hydrogen production through biomass-steam gasification can come to less than $1. That is the thing which the message of the slide. We also have now very widely talked, every day something or other comes on the National Green Hydrogen Mission. And here I want to say that there is a target for how much to be produced. And the investment is more than 8 lakh crore investment is expected. And the green jobs, 6 lakh green jobs also aimed at. So there is a lot of CO2 mitigations portion of the thing. But there is a targeting also, domestic manufacturing of electrolyzer and production of green. Here also the word biomass is not there, but anyway, there is something is there on production of green hydrogen. Maybe there it get included. And now the conclusions. Hydrogen production through biomass-steam gasification is highly efficient than all other process sources. This is one of the important message to be given. We should know it because from all these numbers, that's what the conclusion. And apart from electrolysis, biomass-steam gasification also an important area for green hydrogen production. This is the one to be highlighted, and more focus and support to meet the our targets or policy or green hydrogen mission and all, to make it success. It's very important to have a more focus or support on R&D is needed, because everything cannot come just because to some the technology is not at the lab scale, it's out, but still there is a long way to go. The R&D support is needed for technology finalization and demonstration of biomass-based hydrogen production associated with the hydrogen separation unit, particularly PSA and storage. This is beyond gasifier, and we have to bring those experts also inside. And capacity-based and result-oriented financial support for R&D is very important. Actually, it should not go by either it's a government institute or NGOs and all these things. So it is very much important to consider the private sectors in R&D, similar to education institute or NGOs, based on capacity and result orientation. Actually, this is the thing I want to say through this presentation. And thank you very much. My email IDs and contact details are here. If anyone has any question or anything, even they want to know more about it, they can communicate to me actually. Once again, I give thank SC Skill Council for Green Job and all the one who joined the webinar actually. Thank you very much.
Thank you. Thank you, Dr. Raman, for the very technical and knowledge for the this presentation. Dr. Dhamija, ma'am, you are here. Dr. Dhamija, ma'am. Okay. Before I'll say thanks to you, sir, two questions on the chat box from Mr. Rakesh Bhan. What does carbon neutrality mean for biomass? And second one is, what is ATS gasification system?
Yeah, you see, carbon neutrality for biomass is generally called as carbon neutral biofuel because biomass takes the carbon from atmosphere. We spend quite a lot of money for the carbon sequestration, around $40 to $50 to capture a ton of carbon CO2 from atmosphere. But if we grow any tree, any biomass, saving 40 to 50% of carbon in it actually. So that is the best way of carbon capturing. So even if you put the carbon in atmosphere, CO2 in atmosphere, that is taken into biomass actually. That's why it is called as the, if you put 1 ton of biomass, 1 ton of carbon into atmosphere by burning biomass, and the same thing is captured by biomass. That's it is known as the biomass is a carbon neutral fuel actually. The biomass emitted into atmosphere gets back to the biomass actually. That is one thing. And ATS gasifier is a abbreviation form. Basically the advanced 3-stage gasifier, nothing, right? Because I told you that there is a different stage of reactor. The combustion and reduction makes one stage, and you put the multiple this thing to refine the gas much better actually. So that's how the ATS. ATS is basically advanced 3-stage gasifier system. Basically. Okay. Is it fine?
Yeah. Yeah. Thank you. Any other questions? I'll request participants to, if any question, please ask. Hello, Rohit. Can you
Yes,
give
sir.
the permission to Piyush Jain and?
Sure, sir.
Yeah.
Am I audible?
Yes, sir. You're audible, sir.
Dr. Raman, Piyush this side from Jain Biogreen from Madhya Pradesh.
Good afternoon.
So my question is that during the production of CNG or bio CBG, H2S is produced. So is there any possibility of production of green hydrogen from H2S, which is produced as a byproduct during the production of CBG, CNG?
You see, I'll tell you, the feedstock is having some sulfur more in what is in the biogas plant. In the gasifier, it is not there, and that is also very traces. If you see, I don't know, it may be less than a percentage, I think. So the potential in this bio CNG for the H2S is much less actually. That hydrogen, if you see biogas, at least will have I think 5 to 6% or something. So the availability is very much minimum, almost negligible. So that is not the area basically.
Okay.
Because of the feedstock.
Thank you. Thank you, sir.
Thank you very much.
Rohit, give permission to Jaideep Hirani.
Sir, I already gave the permission to every participants. If
Jaideep ji, you want? ask to any question?
Yes, sir. Hello, sir.
Please.
I am Jaydeep Irani, represent from Imagine Hydrogen, based out of Ahmedabad. My question is, how is it possible to produce zero tars in ATS system?
Yeah.
If we gasify any biomass, there will be some amount of tar is always produced.
Yeah. See, these all are the challenges, as I told you. And when the tar measurement system, we have not got any tar deposition. And how it is possible is, I told you that, the reactor design, since your question is there, you must be well aware of the reactor designs. Reactor has many influencing parameters, and you like residence time and flow velocity, temperature, and the medium in the things, void fraction. There are many influencing factors for the reactor. You optimize the reactor such a way that the complete cracking of the tar happens. That's how it has been done, actually.
Sir, can we use tar reformer?
Tar reformer I could not get, actually. Tar reformer is to filter the tar after the syngas is produced with tar.
Yes, sir. Yes, sir.
See, that I told you there are many ways of removing tar, actually, including the electrostatic precipitator and many of these things. So one of the things can be adopted, actually. But my advice is to produce the gas tar with the, you must be knowing that two-stage gasifier you might have heard, I think, not that Denmark one.
Yes.
They also
claim
20 mg, 5 mg, something like that, actually. So tar removal is not a problem, and the tar, it's better to instead of going for tar reformer and all the things, it's better to avoid the tar from the source itself.
Okay, sir. Thank you, sir.
Thank you very much.
Thank you. Rakesh Bhan, sir, you want to say something? Rakesh Bhan, sir.
Hello, sir. May I ask a question?
Yeah, please.
Sure.
This is Balakrishnan from Chennai.
Okay.
Thank you, sir, for a wonderful presentation. I just want to know what are the challenges in implementing this on industrial level.
Yes, as I told now, because on production side, I don't see any challenge, but the challenge is on the separation and storage level. Already they take, I think, around 3000 PSI or something. The bottling is done, the hydrogen, and the separation using that PSA. I was trying to contacting many people for the to get the even a smaller scale PSA for the experimentals and other this thing, and not much, because right now PSA is being used widely on that for natural gas anyway they are using, and for oxygen separation and other this thing, but getting the PSA, the right supplier and the technology, I found that is one of the big bottleneck on the green hydrogen production from syngas particularly.
Thank you.
Thank you.
Good afternoon, sir. Am I audible?
Yes.
I just, being a layman, I just wanted to know what are the advantages of, what are the usages of green hydrogen in our economy, particularly in transport, in power generation, and how is that achieved?
Yeah, in power generation, one can use the green hydrogen for in micro turbine, and also for transportation, the fuel cell is the best option, actually, because that is the highest efficient thing is available. Because I put one slide on transportation part, actually. Thank you.
Okay, thank you, sir.
Thank you very much.
Thank you, Rakesh ji. And I think now is the time to say thanks. Thank you, sir. Thank you very much.
Thank you very much.
the
I'm very sorry I took a
presentation.
little bit more time because of the more material.
No, it's okay. It's okay. And you answer and question attended very well, and provide your answers to participants very well. And before I'll say finally thanks to you, I would like to thanks to all the participants for his valuable times for joining the webinar. Thank you all. Thank you very much. Thank you, Dr. Raman.
Thank you very much.
Thank you.
Thank you, everyone.
Thank you, sir, everyone.
Thank you very much.